Welcome to Spring LIB.
In the given problem, two wires carrying current I placed at positions 2R and minus 2R. A cylinder, which is placed exactly in the center of the coordinate system, has a radius R and it has a length L. Now we need to determine the net magnetic flux through the half of the cylinder surface above the x-axis. So we need to find out the net magnetic flux through this part. This is the x-axis and we need to find out the magnetic flux through this half. So let's write down first what's the formula for magnetic flux. So the magnetic flux phi of B is shown as B is the magnetic flux dot ds. This is the area element over a certain surface area. Now if I consider this, let's first try to find out the direction of magnetic field at this point. It's flowing direction, as you can. So we'll try to open the actual file. The current through this section is coming out of the page. So I'll put a circle here which shows the current coming towards us and put a cross here to show that the current is going at this point. Look at this section. So if the current is coming out of the page, the magnetic field goes in loop like this. So this is the magnetic field direction. And the same magnetic field goes around and then it comes in this direction. So on this surface, the magnetic field is outwards. Now if we consider this one, magnetic field here goes like this. So similarly on this half, the magnetic field is this way. We can draw the same thing here. So this time we'll draw only the upper half. And then see that the magnetic field goes like this. This is our surface and this is the magnetic field B dot ds. If I were to take a B dot ds, so you can again draw a small sphere. So this is the section of the cylinder. Imagine take a small section ds on this. The ds vector is the area vector of the ds. This is the ds aerial vector, which is going outwards, and that's true at all the points. At all the points, the area vector is always outwards, is always normal to the surface. However, the magnetic field in this region, it's going like this. So effectively, we can say that the dot product of magnetic field with the ds vector is actually just equal to this area, the area along this line, multiplied by magnetic field over magnetic field. And that us. The hint says that we need to find the flux through the portion of xy plane that lies within the cylinder. The xy plane is this. This xz plane. So if this is a x-axis and z coming out of the page, then if we look maybe if you look along from this direction, then it looks like this. This is the axis. So we need to find using this area. So all of this area. Let's try to evaluate the overall. So the magnetic flux due to one wire, let's call it S1, is equal to the is also equal to the one to the other one. This is the surface area. So S1 and S2 are exactly the same in this case. So the net magnetic flux in this case is equal to integral minus R to R I'll explain all the terms once we have written down the entire formula dx. So let's go back and look at x l dx. L is the entire length, which is from top to bottom, the height. This is L. And because the magnetic field due to a single constant and it keeps changing as we go away more and more further away from the wire, the magnetic field due to wire is actually given as mu naught I over 2 pi x, where x is the radial distance from the wires. So the magnetic field along all of this line is not constant. To consider that the magnetic field is different and then integrate over all of that with ranging from minus r distance z. And because we have two wires, the result will be twice of this. Take again minus r to r. Similarly, p of x l dx. We write that as minus r to r once again, mu naught I over 2 pi once again. And now instead of writing x, we know that a wire is exactly at minus 2, or if we talk about this wire or probably this wire, and this is 2r minus x into L dx. Now let's see this. If I take x as 2r, which is this position, if x is equal to at 0, x is equal to we are exactly at 2r, the whole distance. This actually tells us the distance, and because wire is not at which we were using before, this one places the wire exactly at the center, at the center, and is displaced by a value of 2r. Both our wires are actually displaced by 2r. The formula would be 1 naught I over 2 pi into 2r minus. And this, so when we integrate with dx over 2r minus x. That integration is trivial, and this 2 and 2 gets cancelled out. You get a mu naught I L over pi, and the overall value of this is then mu naught I over pi into L of this value 2r minus x. So if I keep r as, this is 2r minus x with limits minus r to r. So by keeping the limits, I get mu naught I over pi L natural log of 3. And that's by considering the fact that if I keep x as r, then I just a value of r, but minus r, then I get a value. And also there's a negative sign, so I should put a negative because x integral is negative. Or I could simply switch the limits, take r on this side and minus on the side, and you still get the